later. Okay, so again, class, I mean, the exam I think is set up for the 9th. I posted it on Moodle, so I think I did. Anyway, so it's coming up. So let's see. So today we're going to work on momentum. Oh, before I get started, any questions, thoughts, concerns?
I wanted to ask you if this, I feel like it was a fever dream, but that survey was real. And I'm assuming you discussed it maybe Tuesday. Did I miss something? We filled out a survey and I was curious what you were going to do with that in terms of discussing it with the class.
I wasn't planning on discussing it with the class. I was going to, well, I mean, I guess it depends on what's in there.
Right. I'm not trying, I don't want to out or, I wanted to give like what's happening. That's all. I know that there's things you either are going to say or not going to say, or not say anything at all, but I was just curious what page we were on.
Oh, well, my intention, I guess it'll have to be, I mean, it's just been a busy week.
Right.
Okay, so my intention is to look at them, read them. The question about, what advice do you have for your other fellow classmates? I was basically going to put those into a giant post and post that to Moodle. I have 2 classes, so I'll probably just combine that for all of my students, so you guys can see what works for your fellow students. Everything else that's like has to do with like questions, complaints, comments about the course. Well, it'll depend what they are. If a lot of people agree about one particular thing, then we'll make a change. If if I got a little bit here, I mean, sometimes there's some things that you'll say that I just flat out disagree with. But basically, I look at it as constructive criticism, and I will take some of the advice and I will push back on some others. So that's just the way it is. So that's the idea.
Thank you.
But it was not a dream. You did fill it. Well, assuming you filled it out, I don't know. Like I said, they're anonymous, so I don't really know what's in there. So, all right, so let's see here. I'm going to share my screen. If I can figure out how to do that. Share content screen. I don't know why it takes a couple seconds to do this. Okay, so let's get, all right, so I started using this program because I like it. What sucks is that you guys can't really see there's a, let me darken the background a little bit. Make the background color, sorry, the pattern color. Okay, let's see if that works. Oh yeah, you can see that a little bit better. Okay, so so today we're going to be, so the objectives today we're going to do, I would call this one momentum equation part 2 or examples, or I think I call it part 2, but really we're just going to work examples. So last class we spent, half the class developing the momentum equation, talking about it. And then this class we are going to just apply it. All right, so the objective today, I really just need to start calling that. Sorry, that noise is annoying. Okay, so we're going to apply momentum equation. No, I'm like texting like Trump. I mean, capitalizing like Trump. There's nothing capitalized about the word momentum. Okay, so we're gonna, this is the linear momentum equation, I should note. And we're gonna do this in combo with, let's see here, what are our tools? Geometry, Bernoulli. Bernoulli does get capitalized. What else? Continuity, etc. Okay, to solve problems. And that's what we're going to do today. How many do I have? Looks like I've got quite a few. I've got 3. Okay, so let's begin. Okay. One of the nice things about working on this board too is I don't have to erase stuff, so we can just kind of move to another area. Okay, so the first problem, this will be example 1 for today. Okay, given. Okay, so we're going to start with forces in bends. Okay, and this is important because you need to stabilize a pipeline. Okay, so here's what's given. This is a vertical bend. Okay, so remember, if it's a horizontal bend, that means it is in the XY plane. This is in the Z plane, so this means it's going against gravity. Okay, so here we go. So it's kind of this weird, like it's a bend, but it's also narrowing. Okay, and so here's our Q. It's going in this direction. Okay, one thing to note, the way I drew these, that means this is inside of a pipe. So the pipe continues from here. It is not exiting into the atmosphere. Okay. And then from this point right here to this point right here, there's kind of like a, distance here of 2 feet. This angle is 45 degrees. I hate 45 degrees. I will never give you 45 degrees on an exam unless I screw up, because the problem is then I can't test if you know your sines from your cosines. Okay, so we are also giving that phi1. So this is going to be 0.1. It's always nice when they give you the points like this. Let's see, so phi1 is 2 feet. Phi2 is 1 foot. Okay, this angle is 45 degrees. Q is 15.7 CFS. I think that's a pretty common number. Pressure at 1 equals 21 PSI. Okay, the mass of the pipe equals 1,000 slugs. And the volume of the water in the pipe is 10 cubic feet. Okay, required. Find force of water on bend. Force of water on bend. Solution. All right. First of all, intuition. Which way is the pipe pushing on the bend? What do we expect? Left or right?
Left.
Okay, so you think the water is pushing this way. Okay, what about up and down?
Up.
Which way?
Up.
Up. Okay, so we think the water is going to push this bend to the left and up. Okay.
But that doesn't work. I mean, unless I'm misunderstanding something, that doesn't necessarily work.
What doesn't?
Is it flowing out of the right end, top right end?
That's what I have backwards right now.
Okay, well, this Q is telling us which way the water is flowing. Okay, your assumptions are going to be these are going to be the wrong guesses, but we'll work it out and we'll see why. Okay, so so the first thing we're going to do here is we want the force of the water on the bend. So what we're going to do, and this is an interesting question because there's 2 different ways we can do this. We can draw a free body diagram of the bend and the water, which is one way to do this. Another way is to just write a free body diagram of the water. But in this case, because we want the force of the water on the bend, we need to separate the water from the bend. So it needs to just be the water. Okay, if I were to ask what is the force to stabilize this bend, then I would draw a free body diagram of the bend and the water. And I'll demonstrate that as we get towards the end. So the first thing here is I'm going to do a free body diagram of the water. Okay, just the water. So I'm not going to spend a lot of time on this because I've got better things to do with my life. Okay, so here we go. All right, now I want to start thinking about forces. Okay, so we got body forces, we got surface forces. Okay, somebody shout out some forces we've got. Okay, what's the body force?
Wait.
Weight, right. Okay, so we got a weight going right here. Okay, and that's the weight of what? The water or the bend?
The water.
Water, right, because this is the free body diagram of the water. All right, what else do we have? Okay, now we got surface forces. So everywhere where I remove the rest of the world, there's a force. Okay, so let's
Normal?
start. Normal, what does that mean in this case?
Well, because we know the direction of the water is going kind of up and to the right, I would assume that normal is still down with weight, but I think that's the wrong assumption.
Okay, let's back up. Normal force means that two things are touching each other, right? So which two things are touching in this particular normal force?
Is it the water in the bend?
Okay, so there is normal force along these walls.
Okay,
We might think of that as pressure. Okay, I'm
right.
not going to worry about that normal force. Okay, and I'm going to explain that in 1 second. What other forces along those walls?
Friction.
Friction. Okay, so we've got two forces. We've got friction going this way. Okay, and I know it's going that way, or viscosity. And I know it's going that way, and I know I got this normal force. I got all that stuff, and the reason that I have all that stuff is because, well, I've got fluid flowing through a pipe. Okay, but the thing is, I'm going to combine all of those into the force of the bend on the water. Okay, and I'm going to do that in the x direction and the y direction. Okay, I'm just going to assume positive force of the bend on the water in the x, Baux, and force of the bend on the water in the z, Baus. Okay, so those are my two, those are just combination of all these little tiny differential forces. And I'm not going to worry about breaking those apart because it didn't ask me to. And there's no way for me to do that anyway. All right, so that takes care of this surface and that surface. Okay, so we got two other surfaces, forces.
Shears, but no shears.
There's no shears because, well, because there's no shears. I mean, because that would mean that the water was flowing along these surfaces, which is not. Anybody? We spent the whole semester talking about this one force so far.
Is it the resultant force?
The resultant force is a combination of other forces.
Momentum.
Momentum is not a force.
Hydrostatic.
Hydrostatic, we're on to something.
Pressure.
Pressure, thank you. Yeah, you know, I mean, obviously pressure is not a force, but it is the pressure times the area. So it's going to be P2 times A2. Okay, and then I've got P1, A1. Okay, so now we've accounted for all of our surfaces. Okay, we got all our surfaces and we did our body force. Okay, so now we know we've got them all. Okay, now we have to deal with momentum, okay, which one of you just mentioned, momentum. Okay, so momentum is going to be accounted for as, I wish I could just erase that red. So the momentum will be accounted for with lines showing where something crosses the control surface. Okay, so we've got, I'll do these in, I guess I'll do it in red. So here's a momentum term here. This is going to be V2. Okay, and I always make sure that they cross the control surface. So that kind of tells me where in the equation I'm going to put these things. Okay, and here's V1. Okay, so now I've got my free body diagram. By the way, y'all need to work on free body diagrams clearly, identifying forces. You know, I shouldn't have had to pull teeth on this one. I mean, I can understand forgetting pressure, but you know, you got to be able to identify forces. Just, you know, saying that. Okay, so here's our free body diagram. Okay, now from last class, I said basically we're going to look for two basic assumptions. One of them is this problem steady? And if we look up here, we were given a single Q. So that means we're basically going to say, yes, this is steady. And then we also want to know, does it have a uniform velocity profile? i.e. does V equal V average for the openings? Okay, and the answer there is we're only given, well, actually, we aren't even given V's. We're only given Q and areas. So we have to assume that this is true too. Okay. If that's the case, then I can use the kind of simplified momentum equation that we've been working on. Okay, so again, how do I know that I'm using the momentum equation? So how do I know? Well, the way that I know is because it's asked for forces on a moving fluid. And the only way you can get at that is with a momentum equation. Okay. If the fluid's not moving, you can use hydrostatics. A lot easier. Okay. So anyway, so let's go ahead and let's so momentum equation, if we can answer yes to both of those questions, can be written as this way: the sum of the forces. Notice I'm going to do X and then I'll do Y over here. Sum of the forces in the Y. Okay, plus the momentum flux is in rho VQ, VXQ. Okay, well, that's usually has a summation in front of it too. Summations in equals summations out of rho VXQ. Okay, so now we just have to identify the forces in the X. So we're just going to spread this out like this. Okay, and so I got, well, let's see here, we got P1A1. I've got P2A2, which is going backwards. And it's at an angle, cosine of alpha. Plus F bow X. Okay, those are my forces. Any questions on that? Okay. By the way, I didn't mean to be too hard on you guys about the finding forces, but my guess is whoever taught this to you did not make you all do enough free body diagrams, and it's just an important skill. So
You care. It's okay. It's what you're asking us to do is we're missing pieces because of obviously the situation. So honestly, it's nice to have somebody care. So I think hopefully everybody understands that you care. It's not that you're even trying to fuss. You're just trying to make us understand that it's important because you care.
Right. Well, I am fussing.
They're a lot easier for me after I've been awake more than an hour too.
Okay. All right. So let's anyway, I also get I just feel bad when I am rude. So anyway, so here we go. So now we've got this is going to be my in terms. I only have one in term. Okay, sometimes there'll be more than one, but in this case, there's only one place where it's coming in. So these are in red, right? I did these in red, these momentum fluxes. Okay, if you have one of those pens or pencils that has multiple colors, it can be nice to draw these in multiple colors, kind of keep track of what's a momentum and what's a force. And so here we're going to do, okay, well, rho for my in is going to be V1. V1, notice it's in the X direction. So I'm going to go ahead and circle. This is the only thing that has a direction on it for the momentum terms. And I did this on purpose. There are other ways to derive this equation that have a lot of different signs on it, and signs become this massive problem. But the Vx is the only place where this has a number like that. And then, well, this is going to be Q1. Okay, one thing that I like to do, I should note right here, you'll see this sometimes in my notes, is I'll put a little plus sign there. That just reminds me that I checked the sign or the direction. Okay, because then when I do the right-hand side, okay, this is only V2, right? That's my only out. So I'm going to get rho. Let's see here. So this is V2, so that's going to be positive V2 cosine of alpha. And this is going to be Q2. Now notice that Q2 and Q1 are the same, but I just put it as Q1 and Q2 for now, just in case, you know, just so you'll be reminded if you're looking at this later, like, oh, you know, I had a problem and it's got 2 Q outs, you know, or 3 Q outs or whatever. Well, you know, you need to separate that all out. Okay, so then this leads to the question. This is nice because this is what we're solving for right here. Okay, so now we need to think about what we know and what we don't know. Okay, let's see here. I don't know my areas, but luckily I can get those. Right, this should have a 2 on it. Okay, and I don't know P2. Okay, I know alpha, I know P1, I know rho, I don't know V1, I don't know V2. Okay, those are all the things that I need to solve for. Okay, so let's go up here and let's do my asides. You guys have probably noticed I like to solve with asides. So let's start with those areas. Okay, aside. Looks like when I solved this the first time, I didn't get the areas, but let's go ahead and do this. So area 1 and area 2. Okay, that's pi on 4, pi on 4. And area 1 is 2 feet squared and area 2 is 1 foot squared. Okay, so this is just going to be pi feet squared. Okay, and this one's going to be pi over 4 feet squared. Those are annoying numbers, but those are exact. I'll leave it like that for now. Okay, we can plug those into this equation. Okay, so now we got this. Now we got this. Okay, any idea how we're going to get P2?
Bernoulli's equation.
Boom, nailed it. Okay, I should have done this. I should have said this beforehand. Okay, and this is this always goes with the asides. Is one of my tools. Okay, and we always have, at least for now, we have 4, I think. Geometry, continuity, Bernoulli. Oh no, I have 5, don't I? Hydrostatics / manometers, which of course doesn't apply in this equation because there's no manometer and all the water is moving. So we're not actually going to use that one for this one. And then 5 is going to be momentum. Okay. So yeah, so we're going to use, so Bernoulli is, if we want pressure, Bernoulli is usually where we're going to get it. Okay. So over here, we're going to do Bernoulli. I'm going to try to keep this drawing. You know what? We're just going to keep this drawing in. We're going to look at this drawing. Okay. So P1 on gamma plus Z1 plus V1 squared on 2G equals P2 on gamma plus Z2 plus V2 squared on 2G. Okay, and hopefully you guys are getting to the point where you know, you can you know, kind of pop that out real quick. Maybe not, maybe you haven't done the homework yet, but this is going to become a very easy equation for you eventually. I'm going to note what's the problem with P1 right now? Anybody?
It's units.
What is it?
It's units.
Yeah, we don't like PSI. Okay, because notice gamma is in pounds per cubic foot. So we need this to be pounds per square foot. Okay, so to go from PSI to PSF, we're going to multiply by 144. So 21 times 144, and we get 3,024. 3,024 PSF. Okay, that's going to make my life a lot easier. Okay, so let's go ahead and we're going to start working this Bernoulli as much as we can. We're going to get stuck, and we have to do an aside for this. Okay, so let's start here. So we've got P on gamma. So it's what's that? 3,024 PSF. Oh, what are our points? Well, in this case, the points are defined by the problem, which is always nice. Okay, so over gamma, which is 62.4 PCF. Okay, so pound per square foot divided by PCF is going to give me feet. Okay, plus Z1 and Z2. How do I get Z1 and Z2?
They're the same.
They're not the same.
Z1 0 and Z2 2 feet.
Yep, yep. So as long as Z2 is 2 higher than Z1, we're good. Okay, so what I'll typically do is I'll draw a line through here, through the lower one, and I'll say this is the datum. Okay, so if this is the datum, then this is 2 feet, then 0.2 is 2 feet higher than that. Okay, so 1 will be 0 and 2 will be 2 feet. So I'll go over here and we'll go, okay, let's, so this is the datum. So it's going to go away. And this one's going to be 2 feet. As long as it's 2 feet higher than the datum, I don't really care. All right, so we'll go plus 0 plus equals. Okay, now we need V1 squared over 2G. Unfortunately, I can't ignore this term. Okay, I'm going to leave the V1 squared out for a second. And then we got P2 on gamma. That's what we're looking for. P2 on 62.4 PCF plus 2 feet plus, and then I've got to do this V2. 2 times 32.2 feet per second squared. Okay, how do we get those velocities? Okay, let's go to our tools. Okay, we've used the geometry. Okay, we're in the process of using Bernoulli so that we can use the momentum. There isn't a hydrostatic manometer. So we've only really got one tool left.
Couldn't you use like the flow rate?
Yes. Okay. So we're gonna refer to that as using continuity. Q equals VA. Okay, exactly. So we're gonna go over here. We say, okay, well, we got this flow rate right here, and I know these areas, right? Pi and pi over 4. So we'll go. So here's my flow rate. So let's see. So we'll do an aside to this aside, and we'll say Q equals V1 A1. Right. So we're still kind of in that asides realm, and Q equals V2 A2. Okay. Let's see here. So Q, let's see, Q 15.7 CFS equals V1. That's something we're looking for. A1 is pi feet squared. Okay. Oh, I don't know why I drew that line. So V1 equals, I think this equals something pretty. Oh, yes, it does. 5 feet per second. FPS, okay, feet per second. Okay, so Q2, I could bother doing all the algebra here. And it's really not that hard, right? Because we just have a pi over 4. So it's just gonna be 4 times as big. But the other thing that I always do instead is I look at this thing and I say, oh, look, the ratio of these is 2. So if I square that ratio, it's 4. So the ratio of the velocities will be 4. Okay, and V2 is going to be 4 times as fast as V1 because it's the narrower end. Okay, so V2 is going to equal 20 feet per second. Okay, that's awfully nice, right? So whenever you see 15.7 CFS, you know, that's because somebody wanted nice, pretty numbers. So they just did the back math. I didn't create this problem, so I don't get to claim to be that clever or whatever. Anyway, so we're going to go back over here to Bernoulli. By the way, this is one of the reasons why if you can't see beforehand what the path of the equations are, like I could work this the way that I would work this because I can immediately see the direction that I need to go. But this is why I like to work with the sides when teaching you guys, is because when I work it, I just immediately look at it. I know which equation I'm going to need. I know which quantities I need. But you guys, it's your first time through, so you may not be able to do that. So what can be helpful sometimes is to like take your sheet of paper and just like fold it in half or whatever, and just say everything on the right-hand side is going to be my asides. That's going to be like, I'm working through my equation and I suddenly realize I need some quantity and I have to go and do Bernoulli or I have to go do continuity or whatever. So I try to work these, not the way that I would work them, but the way that I think that, you might kind of approach them. So it's good to think about, just kind of separating off an area of your paper so you can go and solve for things that you need for the main equation. Anyway, so this is going to be 5 feet per second. It's going to be 20 feet per second. Okay, so we could solve this right here if I wanted to. Like we could just plug all this into the calculator. I'm going to leave this open for just a second, because I like to think in terms of orders of magnitude here. Unfortunately, when I did these notes, I did not keep 5 sig figs. So we're just going to have to, so we won't have this perfect like that. Okay. I want you to just note real quick, okay? In this particular bend, right? This is all about energy, okay? So we had to, as we traveled from 1 to 2 in this particular bend, as we went from, here to there, okay? Notice I had to raise the fluid by 2 feet, okay? But I also had to add the amount of kinetic energy by almost 6 feet. Okay, so that was more important in this particular problem. The kinetic energy transformation or increase was more important than the potential energy increase. However, note that total, I had to add about, almost 8 feet of head to this fluid. So where is that going to come from? Well, it's going to come from the fact that I'm going to lose pressure in the fluid. Okay, so P2 is going to be less than P1. Okay, so if I solve this, I'm going to get P2 equals 2536 PSF, 2536 PSF. Okay, so basically I lost pressure, and that pressure was converted into elevation and velocity. Okay, so that's the pressure that we're going to work with. Now note we compare that pressure to this pressure right here. If I wanted to, I could divide by 144 and compare it to the original, what do we have, 21 PSI? Yeah, 21 PSI if I wanted to, but there's no real reason to do that. Okay, so now we've got the pressure. So let's go back down and let's keep in track what we're looking for here. So we've got P2, we've got V1, we've got V2, we've got everything we need. At this point, this is just an algebra equation. I'm gonna kind of just plug and chug here at this point. But at this point, hopefully you guys can see how to solve this. Okay, so let's see here. P1, where's my, oh man, interesting. Okay, I did this all weird, but that's okay. Okay, so P1 is 3024 PSF. Okay, notice the area is pi over 4. The diameter was 2 feet squared. Okay, so PSF is balancing square feet, so you'll get pounds. Minus P2A2. P2 was 2536. 2536 PSF. Okay, times its area, which is pi over 4 times 1 foot squared. Right, and then that's going to be cosine of 45 degrees. Plus F bow X. Okay. Then I'm going to add one more term, rho V1 Q1. Okay, so anybody remember the row of water? Anybody know how to get the row of water if you forgot the row of water?
Like 1,000.
Okay, if we were in the SI system, by the way, perfect.
19.4?
Ooh, close.
92.4, isn't it?
Hold on. Wait, what? 92.4? 19.4, 62.4. Somebody, Caesar just typed in. Okay. I wanted you to make these errors in 1,000. I'm not sure which is the closest. I think maybe these two are the closest. This is close. This is way off. Okay, right. It's the one on the formula sheet that isn't right. Thank you, Stephanie. That's exactly right. Okay, rho does equal 1,000, but that's in terms of kilograms per cubic meter. Okay, so we can't use kilograms per cubic meter. Dominic, thank you. Like this is like the most common error that I get. So just be aware of that. We can't use that because this system is not SI. Okay, so that's a great error. I don't know where 92.4 came from, but it's, my guess is you're just mixing up some of these numbers. Okay, 19.4 is very close, but it's off by a decimal. And 62.4 is pounds mass per cubic foot, or it's pounds force per cubic foot. So either, not equals. So we can either say that this is, let's see, so this is gamma, that's the specific weight. And this could be density. Okay, but you guys should know by now, we don't use pounds mass in this class. Okay, so for density, we need slugs per cubic foot. Okay, so what you need to do is you need to remember this 1.94 is right, but you're off by a decimal place. So what you need to do is if you get stuck, you remember that gamma equals rho G. Okay, so gamma looks like this, 62.4 PCF equals rho times gravity 32.2 feet per second squared. Okay, so rho equals 62.4 divided by 32.2, which is 1.94. Okay, and this is slugs per cubic foot. Okay, and as I think it was Stephanie wrote in, it's wrong on the equation sheet. On the equation sheet, it's given to you like this. Okay, if you plug a pound mass into that formula, you're going to get it wrong. Okay, so I'm taking a moment to warn you. Okay, but I'm still giving you that equation sheet. So you're going to have to make note of that. So when you're doing your homework and you pull that equation sheet out and you see this thing, you need your little alarm bells need to go off in your head. Okay, and you might be like, well, why are you giving that equation sheet? And I'm like, because that's what they're going to give you on the FE. And when you take the FE and you see rho equals 62.4, I want you to say to yourself, divide by gravity. Gravity is 32.2. Okay, so all right, so that you can get it in slugs, or else you're going to get the wrong answer here. Okay, so I'm making a kind of a big deal about that. I didn't really expect that anybody had it memorized, although somebody was close. 19.4 is pretty close. All right, so here we go. Rho 1.94 slugs per cubic foot. Okay, and you don't need more than 3 sig figs here. If you do 62.4, you divide by 32.2, you'll get some extra numbers, but don't worry about those. Okay, V1, which was what, 5 feet per second? Yes, 5 feet per second, and V2 is 20 feet per second. So this is going to be, let's see, 5 feet per second. Q is 15.7. CFS equals 1.94 slugs per cubic foot times 20 feet per second times 15.7 CFS. Okay, so let's see. Yeah, so if we plug all this in, the only thing that I want you to be aware of here that's annoying, okay, is we always need to check our units, okay? And I always like to make this as, to remember that force equals mass times acceleration. So in the SI system, that's newtons equals kilograms meters per second squared. But in, the British system, or really the American system, it's pounds equals slugs per foot, or slugs times foot per second squared. That's why we need to do this in slugs. So our pounds are coming from slugs, foot, seconds, seconds. Okay, that's a pound. Slugs, foot per second squared. Okay, that's where our pounds come from. Okay, and then this cubic foot right here is going to cancel with this cubic foot. Okay, and this cubic foot is going to go with that cubic foot. Christian, would you mind speaking your question, since I'm I can't read those while I'm going.
I was just curious about what happened to the cosine alpha that comes after V2.
I forgot
Okay.
it. Sorry, and I'm making you speak up because because sometimes I look down and I see the chat's got like 10 comments and I'm like, I'm too busy talking. So I just miss all that. All right, so this we end up with F bow X. So remember, my terminology here is force of bend on water in the X direction is negative 7813 pounds. Okay, so that's how we do this. You will note also algebraically, like if you guys get online and you start looking at the way other people do this, a lot of people will combine these two terms, okay, on the same side of the equation and pull out the gamma. I mean, we'll pull out the density, we'll pull out the velocity. And sometimes they'll pull out the velocity squared since there's a second velocity in this term right here. So you'll see this written as rho v squared a. And you will see that. You can do that if you want. I just don't do it that way. I just think it confuses my students more than helps them. So, but you can. Okay. All right. So that's it. All right. So now we're going to go to the y. Wait, any question on the X direction? Okay. Note. I've forgotten what the question is, but this is the bend on the water. If I want the force of the water on the bend in the X direction, okay, then it's going to be 7813 in the other direction, right? Okay, so just kind of keep that in mind. Okay, and again, that's my terminology, bend on water, water on bend. If you want to do a different one, you can go for it. What I don't like is a lot of people will do this. They will just write f of x. In fact, if you look at some of my old work, you will see me writing f of x. The problem is then you're doing the sum of f of x. And one of the things you're plugging in for the sum of forces in the x direction is the force in the x direction. And I don't think that that's very helpful. So to me, it's better to, if you do computer programming, it's better to create variables that are clear, that take you another split second to write out, than to write ones that are very simple. So like if you start coding on a computer and you just decide you're gonna call everything X or Y, eventually you're gonna forget what X and Y are. So it's better to call it like A for area, or, A underscore pipe, so area of the pipe, or whatever. Anyway, just something to consider. All right, so let's do.
I had a quick question.
Sure.
That negative does indicate that we assume the wrong direction, right?
That's correct. We assume the wrong direction.
Okay.
Okay, but that's why I always assume a positive direction, because that's just gonna, so then assuming the wrong direction, I get a negative sign. That means both things in that case, right? But if I assume a negative, then that means it's a positive, right? So, yes, I guess the other way to do this normally would be to go F Baux equals 7813 that way, right? And F Baux equals 7813 pounds that way, right? So depending on who taught you statics, Dominic, I know who taught you statics, but some people will ask you to just put the little arrow in, which maybe I should have asked my students to do that, but I didn't. All right, so let's do the vertical direction. Sum of the forces in the X equals, oh, we forgot, plus the summation of the ends, rho v q. Okay, let's see, this is going to be Vy. Okay, again, noting this is the only thing that has a direction in the momentum term. Okay, equals sum of the outs, rho v q. Okay, and I'm going to go ahead and put a y right there. Okay, so let's go ahead and look at this thing. What forces do we have in the y direction? Somebody want to shout them out? Shout one out. There's my free body diagram.
Wait,
Weight, right, okay, and that's the main difference between these two, is I've got the weight of the water. That's negative. What else? Are there any other arrows on this thing? Blue arrows? in the Y direction?
F bow.
F bow Z, so bows, it's F bows. Okay, I've got one more.
P2, A2.
Right, okay, minus P2, A2, sine of alpha. Okay, notice again, and I need to reiterate this, pressure is always pushing. Okay, pressure is always pushing. I guess that's not technical. I guess you could have like negative pressures, but you still draw the arrow pushing and it's a negative pressure. Now, in an absolute sense, all the pressure is pushing, but in that case, it's equivalent the same as a pull as far as the net effect. Because what it really means is that there's a pressure on the other side somewhere that is positive or that is pushing harder. Anyway, okay, ins in the Y direction. Do we have any ins? Okay, notice now we're looking at these red arrows, red, red. Okay, so these are my velocities. So as a V1 is in. Okay,
Right, you're right.
go ahead.
I was trying to say, it looks like it says P1A1, but you want to call it V1, I'm assuming?
What?
In the blue arrows, you have P1A1, but in the red arrows, it's going to be V1 to go in the
Right.
Y direction equation. Okay, I wanted to make sure I was reading the diagram properly.
You are, so there's pressure on this surface is P1A1, but the fluid is flowing across that surface, and so that's V1.
Okay, thank you.
All right, so note that neither V1 nor P1A1 are in the Y direction. So we don't have anything flowing in the Y direction. Okay, in the Z direction, however, we've got V2 flowing out. Okay, so I'm going to do rho V2, which is, so in this case, positive V2 sine of alpha. Now again, remote note that I put my little plus sign in there. It's not necessary, but it just kind of helps me keep track. Okay, and then Q. Okay, so now I'm basically all ready to go because we've already done this. The only thing that we need, the only aside that we have is, how do we get the weight from what we have up here? How do we get weight in fluids class? In the other classes, it's mass times gravity. How do we get weight in this class?
In volumetric flow rate.
No, just because the water is moving doesn't change its weight.
Volume and density.
Volume and specific weight. Okay, so what we're going to do is we're going to say, okay, let's just go ahead and do that over here. So we've got a volume of water, 10 cubic feet. That's the volume inside the bend. So weight equals gamma water in this case times the volume of water. So this one can be done in our heads. Okay, remember the gamma. What's the gamma of water?
$62.4.
Yep, 62.4. Sorry, I'm gonna try to keep remembering to ask you guys that. It's the sort of numbers that once you've done this a lot, they just kind of stick into your head. Okay, 624 pounds. Okay, so comparing that to what we got going on here, it's not unimportant, but it's an order of magnitude smaller. Okay, so let's go ahead and we're just going to plug all those numbers in. Let's see, so this is negative 624 pounds plus F bow Z minus P2A2. We've done this already. What was all that? We did this over here, right? P2A2. This is this right here. All right, so 23, 25. Dang gummits. I'm losing my work here. 25, 36 PSF times A2, what was A2? A2 was pi over 4. That's pi over 4 feet squared times the sine of 45. Thank you, Christian, because I would have messed that up there. Equals the rho. Now remember the rho is 1.94. slugs per cubic feet. Okay, plus V2, which V2 is 20 feet per second times the sine of 45 degrees. And then the Q, which is 15.7 CFS. Okay, or CFS. Okay, so biggish equation. And okay, let's check our units here. PSF times square feet gives us pounds. Slugs feet per second squared. That's my pounds, and then the cubic feet cancel. Okay, so I'm gonna get pounds. Okay, so if we solve this all the way, I'm gonna get Fy equals 2463 pounds. No, not Fy, F bows. It always makes me think of the Nintendo turtle, bad turtle, Bowser. That's interesting. We've got a positive number. Oh yeah, okay. F bend on water, Z. Okay, so I could also write that as F bows equals 2463 pounds up. Okay, and I could say F wobs, water on bend in the Z is negative 2463 pounds. Or I could go here and I could say F wobs equals 2463 down. Okay, equal and opposite. Okay, so let's see. Okay, yeah, we're doing okay for time. All right, so what I want to drive at here is okay. Bend on water in the Z direction, bend on water in the X direction. Okay, let's take these one at a time. Our intuition up here was these were my guesses. Okay, I don't remember if I was asking which way the water was pushing on the bend or the bend on the water, but let's think about this. Okay, bend on the water in the X direction. Bend on the water in the X direction. Well, the water is cruising along here, minding its own business. Okay. And then all of a sudden it hits this bend over here. Only way that bend could have pushed on that would have been back to the right. Okay. Hence its momentum in the X direction changed. There was no way for this thing to like somehow accelerate it in the, yeah, that's actually not entirely true. But anyway, so this is the force of the bend on the water is in fact in this direction. Okay. And then the other thing is, what about the force of the bend on the water in the Z direction? Well, notice we got a positive number for that. And think about it this way. It came in, it had no momentum in the Z direction. And then it leaves and it's got some momentum in the Z direction. Where did that momentum come from? Well, the bend had to push on it. The other thing the bend had to do is it had to hold up the water itself. Okay, so so that's the two, that's the weight of the water. So that's why this kind of has that direction. Okay, now on the other hand, the force of the water on the bend, okay, the water is pushing the bend in this direction. Just because it's like there's basically something in the way of the water. The water wants to just keep going right forever. And then the water is pushing the bend downwards. And that's really kind of hard to see. I don't really have a good way to describe that. I think if you're a biologist, they would call this an acceleration reaction, which is meaningless to me. But it's just, it's easy to just think about it, equal and opposite. So, the bend is pushing the water up, so the water is going to push the bend down. It's coming here and it's hitting and it's bouncing that way kind of. So the net effect is to move the bend that way. I don't know. Anyway, that's how I think of it. So anyway, in this particular case, for this problem, what did we ask for? We said, what is the force of the water on the bend? So force of the water on bend equals the square root of this one, and that one squared, which I'm not gonna work for you guys. I know you can do that. And we get 8,192 pounds. And then we need to get the angle, theta equals the inverse tangent of this one, negative 2463 pounds, over this one, 7813 pounds. Okay, and if you do it like that, it'll actually take care of the sine for you, 17.5 degrees. So in this class, we would say force of the water on the bend equals 8.19 kips at an angle of 17.5 degrees. Okay, and I'm assuming you guys know how to do this. All right, so let's see what we can do with these other problems. Oh yeah, okay, so in this case, I just wanted the force of the water on the bend. So when I drew my free body diagram, I drew my free body diagram of the water. For this next one, I'm going to ask for something slightly different. Okay, and so we're going to get a slightly different thing to work with. Okay, so wait, okay, yeah. Please interrupt me if you have any questions. Okay, so this is going to be example 2. And this one is going to be, again, it's going to be about anchoring forces, which is very often how we do these. All right, so this is one of those nozzles that you see in your science lab, where you've kind of got like a, a nozzle coming down like this, or you got a hose coming down like this, and then there's like a nozzle built in on the end of it. Somebody asked a question about the nozzle not that long ago. Anyway, so right here, this opening is 5 millimeters. Okay, always when you see millimeters, immediately think, okay, I'm gonna have to convert that to meters. Okay, this is 16 millimeters. Okay, and then what do we got? Okay, so this is given. Okay, Q equals 0.6 liters per second. Nobody likes that. The mass of the nozzle itself is 0.1 kilograms. Okay, we're fine with that unit. The mass of the water in the nozzle is 3 times 10 to the minus 3 kilograms. Okay, so very small in the grand scheme of things. And then P1, and luckily they tell us where P1 is. That's right here. Is 464 kPa. Okay, so then the last bit we want is, so this is required. We want to know the force to anchor. Okay, this is the force to anchor the nozzle. Okay, and before I get into this, let's see. I want to just discuss real quick. There's two kind of competing forces here for this nozzle. Okay, one, first I'm going to draw my control volume, right? And my control volume is going to be right here. I'm choosing that point 1 because that point is like given to me. They tell me the pressure there. I know information there. And I'm going to kind of go around this whole thing like this. That's going to be my control volume. Okay, I'm going to assume that the weight of the nozzle in the water is not really important, but basically I'm going to have a pressure at 1 that's going to be pretty high. That's going to be pushing downwards. And so that's going to cause the nozzle to want to fly off. Okay, on the other hand, I've got this water which is being accelerated through there. So there's this jet of water leaving at point 2. Okay, that's going to have way more momentum than it has at 1. That's going to cause it to want to like jet upwards. Okay, so it's kind of competing forces here. I have a feeling, and probably your gut should tell you that the pressure at 1 is going to be greater than that momentum, right? But let's just go ahead and work this. Okay, now I want you to notice that this is the F to anchor the nozzle. So the force to anchor this nozzle, where that force is coming in is basically, there's probably some threads along here and the nozzle probably like screws in. So that's really where that force is. Okay, so when I'm drawing this free body diagram, I'm going to include the nozzle on this thing. So free body diagram of water and nozzle. Okay, because I want the force of the anchor on the nozzle. I want to, yeah. So the force of the anchor is probably in those things. So it probably looks like this. Or something. Yeah, that's terrible drawing. Because it's not really that important to be perfect. And I make no aspirations to perfection, but there are still limits. Okay, so something along those lines. Okay, so then what we need to do is we need to identify forces. Okay, so I'm going to do my forces in blue again, just because I have different colors, so I might as well use them. Okay, so I've got weight of the water. So I'm going to start with body forces. I've got the weight of the water. And I've got the weight of the nozzle, which I'm going to draw over here, even though it's really acting at the centroid, which is probably over by where I wrote the weight of the water. Weight of the nozzle. Okay, I include both of those because it's the free body diagram of the water and the nozzle. Okay, so it's important to identify what you're drawing the free body diagram of. Okay, other forces. Do I have any pressures? Let me ask you again. Do I have any pressure?
I think they have a P1.
Yeah, we have a P1, right? So, and that P1 is right here, right? It's all along this surface right here. What about P2? Do I have a P2?
Sure, you have to use Bernoulli's equation, right?
We could, but I don't think I'm going to. Why not? Look at something special about the way I drew this. Okay, this is a nozzle, right? So this is like one of those faucets you have in chemistry class, right? Well,
You can use your diameter ratios.
no, well, we can do that to get the V2, but what are we thinking about here instead? Like this is something more basic. What's the pressure at 2 if 2 is going out into the classroom?
Oh, 0.
0. Okay, so always look for that. So in this case, I could draw a P1A1 like right here if I wanted to. But notice that I'm just going to say that it's 0 gauge. So there's no real reason to do that. Okay, so we won't do that. I shouldn't have just undid that because that means in the recording, it's not going to record it at all, which is really annoying. Do we have any other forces?
Friction between the nozzle and the water.
Okay, excellent question. Turns out that it's incorrect, but yes, I mean, like exactly the right instinct. Go ahead, Stephanie.
Do they cancel each other out because we're doing both of them in the diagram?
No, because the net effect of the friction on the water and say the normal forces along, the pressure between the walls will be upwards, the net effect. However, all of that is taking place like right in here. Those are internal forces to our diagram. Okay, so over here, we drew the water itself. So we had the force of the bend on the water, the force of the bend on the water. Okay, but here, I drew the nozzle as well. So this is inside that diagram. So we can't even resolve that. Okay, but right now I've got 3 forces downwards. Well, I haven't done the momentum terms, which we would do in red. Should be a V. Sorry, this is a 1. Sorry, this would be a V1. Okay, so this is going to be P1A1. Okay, so I haven't even drawn these yet, but what about these? What about these little things over here? What about these little teeth? Okay, that's like a screw, okay? And that is a force of, we're gonna assume it's going upwards. Well, this is the anchoring force, okay? And that is where anchor, I'm only gonna do it in the Z direction because there's not gonna be anything going on in the X direction. Okay, so if you'd wanted to, you could have drawn the water, right? You could have done, I'm gonna do the force of the anchor or the nozzle on the water. And then once I'd solved that problem, then I could go back and say, okay, I've done the force of the nozzle in the water. I've solved for that. Now I want to figure out the force of the anchoring. So I need to do another free body diagram of the nozzle itself, but that's just complicated. So we're going to do it like this. Does anybody have any questions about these forces?
The only question I have is you have a lot of cool science videos on Moodle. Is there anything we can look up in terms of like, once this problem is done, we can apply it or we can see it with a video? I was curious if you had anything.
If I had anything like what? Say it again.
If you had like a video representing this math problem, does that make sense? Like,
Well, you can either go back and watch this video, or if you go down to like, I don't know, lesson videos or something, somewhere on Moodle, I have recorded all of these because last semester I recorded them all. So I have a.
no, I'm asking about water, like what we are about to do is about the forces and why the nozzle changes the problem. And I was curious if there was a YouTube video that shows you the application of the equation. I understand what we're doing. I'm asking if there's I'm trying to think what video we watched a couple weeks ago, but I was asking if there was a video that shows this in the real world, the water flowing through the nozzle and what the equation is applicable to. Makes sense?
I'm not sure. I can say that in this case, as far as what it's applicable to, it's applicable to any time you have moving fluid.
Right. I was just curious because like that's the whole idea of pressure and nozzles and the reasons you use them. I was curious if there was a video on that. The way it completely, does that make sense? I don't think I'm making any sense, but
Well, at the moment, I can't think of one. So let me
go ahead.
let's
Go
finish
ahead.
this and we'll hang out afterwards and we'll talk about it, see if we can figure it out. Okay, so I'm gonna do this forces into Y. Okay, so I've got F anchor. Okay, I've got minus P1A1 minus the weight of the water minus the weight of the nozzle. That's all my blues. I think that's all my blues. Yeah, and that's why drawing a free body diagram is key, because once you do that, all you got to do is take this equation and then stare at the diagram. Okay, plus, okay, I've got an N and that's V1. So I'm going to do rho Vy. Okay, so that's going to be negative. Okay, because it's going downwards. V1. And that's going to be Q. Okay, I'm only going to use one Q here because it's the same Q for both of them. Okay, but again, remember you'd have to split that up if there were multiple Qs. Okay, equals. Okay, rho negative V2 times Q. Okay, so when I grade your tests, if you guys haven't noticed this is what I'm looking for. I'm looking for this equation, and then I'm just going to see that you plugged in numbers. That makes sense. Okay, this is the one, F anchor is what we're looking for. P1 is given. We can get A1, that's pretty easy. The weight of the water and the weight of the nozzle, we can get those because they gave us the mass of the nozzle and the mass of the water in the nozzle. So it's just mass times gravity in this case. That's pretty rare to do it that way in a fluids class. What's the rho of water in this case? SI system? No. Dominic?
9810.
No. Rho.
Oh, 1000.
1000. Okay. V1 and V2, we're going to get from continuity from Q equals VA. Okay. So let's go ahead and get V1 and V2 because that's going to be the only real problem here. I will never give you liters per second on a test. If you ever have a liter on a homework, you're going to do what I would do, which is you would look up the conversion. In this case, this converts to 0.6 times 10 to the negative third cubic meters per second. Okay. So then we'll get V1 and V2. So V1 equals Q over A1. V2 equals Q over A2. Okay, so this is going to be 0.6 times 10 to the negative thirds cubic meters per second. Okay, and this is the same 0.6 times 10 to the negative third cubic meters per second. And then the areas pi over 4, pi over 4. And we don't have, these things are not easy multiples of each other. So 0.016 meters squared, 0.005 meters squared. Okay, this is also a common mistake, is getting the wrong number of zeros there. Okay, so this is going to be equal to 2.98 meters per second. And this one is 30.6 meters per second. Okay, it's speeding up quite a bit. Okay, a factor of 10. Okay, so we'll go down here and I think we're ready to plug everything in. Okay, this would have been an easier problem for these particular things. So, you know, for a momentum equation, F anchor. By the way, I'll usually only ask you one direction. I usually won't make you do X and Y on an exam. So minus P1, which was 464,000 pascals. Okay, notice we had pascals, we had kPa. Nobody likes kPa. Times pi time over 4 times 0.016 meters squared. Okay, minus the weight of water, which is like super small, 3 times 10 to the minus third kilograms, times 9.81 meters per second squared. Okay, minus the weight of the nozzle, minus 0.1 kilograms, times 9.81 meters per second squared. Okay, let's see, keep going, plus, okay, the rho, 1,000 kilograms per cubic meter, times negative V1, 2.98. Okay, Q was given as, I forgot what Q was. What was Q? Oh, 0.6. Times 10 to the negative third cubic meters per second equals rho 1,000 kilograms per meter cubed. You know, these things really get long. Negative 30.6 meters per second. 0.6 times 10 to the negative third cubic meters per second. Okay, whole lot of junk. All right, so let's see, F anchor. Again, for teaching purposes, I like to kind of, you know, get some numbers in here. Let's see here, minus 0.09329 kilonewtons, minus, looks like when I did this, for whatever reason, I did this in that can't be right. Oh, interesting. Okay, I don't know why I did it that way. Give me a second here. 1, 2, 3, 93.29 newtons minus 0.02943 newtons. Let's see. Minus 1.788 newtons equals 18.36 newtons. Oh wait, I'm missing one, sorry. Minus whatever, what is that? 0.981 newtons minus 1.788 equals 18.36 newtons. Okay, so the point here is, the reason that I wrote that out is just to make the point that this velocity, the velocity exiting, is way bigger, 100 times bigger than the velocity entering, the momentum term is 100 times bigger. So this term basically doesn't matter. These weights don't matter, not in any real sense. The only thing that really matters is this pressure term, which is being modulated slightly by this exit term right here. So F anchor equals 77.7 newtons. Okay, which is basically almost all resisting this this pressure. Okay, so sorry went over. We're about 2 minutes over. I seem to go over every day these days. I teach a lot slower online. We would have gotten another problem done in person, I mean in class, but anyway, questions, comments?
Would you have added that 93? I think I'm
What do
looking
you-
at it wrong.
What do you mean?
Never mind, I got it.
Yeah, something's, oh, there should have been a negative on that 18. This should have been a negative.
That's what it was.
Yeah, you're right. Yeah, yeah. And I'm pretty sure that that's 1.7. Sorry, I'm converting my notes in my head as I go, because my notes I did this slightly different. That's 17. Yeah, it's gonna go to the other side and be positive. Yes, that's good. Okay, so any questions? So you'll know my favorite problems on these really are like the bend that we just did. But usually what I'll do is I'll have a bend that comes in like this and leaves, you know, and maybe it's narrow here and wide here. Okay, and I like to do it like that because then we've got a pressure here. We've got a pressure here. We've got velocities here and here. And so it will force you to use Bernoulli. It'll force you to use the weight of the water. It might force you to do the weight of the bend, depending on whether or not I want the forces on the bend or the forces on the water. And I just love these problems. And of course, it's got an angle on it, which is always good, say 30 degrees or something. So those are my favorite types of problems. So, but it can all be done with what we just did. Also, it's got a negative velocity right here. So this one has a negative X velocity and a negative Y direction velocity, which I like because it forces you to think in those terms. So, and so that's it. Any questions? Okay, well then I'm gonna go and I will, I'll post this video later and I'll be here in office hours at 3:30. Nobody's saying anything. Okay, well, I'm gonna stop recording. That's gonna be the first thing I'm gonna do. So if anybody wants to say something really mean, they can do it then.
I have sort of a non-class related question.
Sure.
How many professors teach structures?
Ooh, I don't know. I think it's just Egaselli, but I could be wrong. Are you taking that right now?
I'm taking it now. Didn't do so hot on the first test, so I was thinking about dropping it to try to get a different professor